And we're gonna go. Welcome, Jim Bergmann.
Hey, how you doing? Well, we're gonna go over a little bit on vacuum and evacuation, probably one of my favorite topics. So, now you guys are gonna be like seeds I'm gonna plant. You gotta take this information and disseminate it throughout the industry. Because it's like a lost art, I swear it's like, we haven't learned anything new here. It's just like rediscovery of something old. And, we're really bringing vacuum and understanding of vacuum back into the industry. So I got a pretty good presentation on it. Back in 1959, this review of vacuum for service engineers was published. It was written by guys that were in the vacuum industry that were really trying to transition people in scientific vacuum over to HVAC. And one of the quotes there's things a lot of us, which some of us know something, some of us know a lot, and things which none of us know enough. And this is honestly a subject none of us know enough about, because it's like a lost art. And Dan Houlihan is probably one of my favorite guys, and he's one of the guys that the dead men are the people that the keepers of the lost arts. There's so much we just take for granted today on how our industry works and what's going on. So we're going to go over some basics. I think the first thing to understand, because I'm going to walk you through a little journey here of understanding vacuum, okay? And you're going to have to open up your mind a little bit, because it's not intuitive to what you've always thought, you know. So, like, if you start, first thing is pressure always pushes from high to low, period. Just like heat transfers from high temperature to low temperature, pressure only pushes one direction, from high pressure to low pressure. And vacuum pumps, all they literally do is they sweep away some atmosphere and create an area of low pressure, and then that pressure in the room or the pressure in the system rushes into that pump, right? And so air gets actually pushed. When you're vacuuming with a vacuum cleaner, the atmosphere is shoving the dirt into your vacuum cleaner. The vacuum cleaner does not suck, okay? Pressure only pushes one direction, from high to low. Your vacuum creates an area, it sweeps away some of the molecules. The remaining molecules room, just shove in there to take up that space, and that's it, right? When the pressure becomes so low, eventually it just stops, right? Because in order for air to travel through a pipe, through a door, through anything, it's got to have a pressure difference, right? Just like we've got to have a temperature difference for heat transfer. So when you're like looking at an air conditioner, you're seeing the condensers getting bigger and bigger and bigger, and the condensing pressure's dropping further and further and further. You go, oh, it used to be back when we were in school, was, you know, condensing temp over ambient was 30 degrees. It was 30 degrees higher. You're going to take your outdoor air at 30, that's your approximate condensing temp. Then came along the 10 to 12 SEER, that dropped down to 25. Then came 13 SEER and dropped down to 20. Right now we're at 17 plus SEER, and it can be as low as 10. You go, shit, man, once you get it down to 0, it'll be perfect. Condensers will be huge, but if it's 0, heat transfer stops, right? We got to have a temperature difference for heat to transfer. We got to have a pressure difference for pressure to move. Just to put this in perspective, right? Because people always talk about like space being in a vacuum. Well, why doesn't it suck our pressure away from our atmosphere? So in a vacuum, we should all be dead, right? It doesn't work that way. The sun hits the earth, it heats the earth up, it generates pressure. Those gas pressures push as far as they can into space, and they stop. That's it. Space is just an empty void. The pressure on the earth is highest at sea level, and it pushes as high as it can. And when it can't push any further, which is about 60 miles up or 56 miles up, that's when our specific weight of our air is 0.00000000000.620 pounds per cubic foot. It's very low, all right? And that is deeper than any vacuum we can get on Earth. We cannot achieve a perfect vacuum on Earth. We're talking about probably like 6/100ths of a micron or so, and we're talking very, very low pressures on there. A couple other terms I want to talk about. Vacuum, we're talking about vacuum, it's just any pressure lower than atmospheric pressure. We said nature creates a higher vacuum than we contain on Earth. A state of high vacuum is also a state of low absolute pressure. And here, the deepest vacuum was 0 psia, negative 14.696, 29 inches of mercury, 0 microns. But it's important to realize that on all the systems we work on, all we can achieve is a partial vacuum. And in our industry, when you guys say, I'm down to 100 microns, that's nothing. That's roughing vacuum, right? When you get into scientific vacuum and turbomolecular pumps, I mean, they start at 0, where they say that's the start of a vacuum for them is 0 microns, right? We're way, way above that. We're in an industry all we're trying to get is the moisture and the gases out. Right, evacuation is just removal of the free air, nitrogen, moisture. And our work, when we're talking about free air, it's the air that comprises our atmosphere, which we freely breathe. Okay. So here's now we got some basic terms on the way. Here's the next thing you got to understand. And just think of this for a minute. If we took that tank, that 100 cubic foot tank, let's say we just filled it with water first, right? I have a 100 cubic foot tank of water, and I pump it out at 10 cubic feet per minute. In 10 minutes, the tank would be empty. There'd be no water left, right? But with air, it's completely different. If we have 100 cubic feet of gas, and we pump it out at 10 CFM, there's still going to be 100 cubic foot of gas in that tank if we pump it out for 10 minutes, 10 hours, or 100 years. Right? We cannot get all the gas out of that tank, and the gas is going to continue to fill the remaining space in the tank. All right? There's fewer and fewer molecules, so the air density drops, but the remaining molecules are going to occupy the entire space of that tank. And we're talking about literally millions of molecules when we're down at 100 microns, or it's way beyond what we could ever count. Vacuum also, poor conductor of heat. All right, this is how we actually use, this is on the end here is a thermistor vacuum sensor. And that little curved piece is inside of the vacuum gauge. If you were to look, I actually brought a vacuum gauge with me here, in case you've never seen one before. In case you're brand new to this industry. Right, so if you're looking, oh, let's see, you brought your dues.
Oh, absolutely.
Thank you. If you look inside this hole right here, right, inside the hole is that sensor. So what you're looking at is if you look just inside here, you'll see the end of that. That little thermistor on there is about the size of a grain of pepper, and that actually in your vacuum gauge gets up to about 300 degrees Fahrenheit. So as soon as you turn on your vacuum gauge, 300 degrees Fahrenheit, that little bead is. If you touch it, it would burn the crap out of you, right? Not very long though, because it's very small, but it would hurt. And so that is generating heat, and the rate of heat transfer away from the thermistor is going to dictate its current flows. They're trying to keep it at a constant 300 degrees. A lot of air around it, the air sucks up the heat real fast, and they got to provide a lot of current to the vacuum gauge to keep the thing at 300 degrees. They convert the current flow into a representation of vacuum. So the deeper and deeper the vacuum gets, the less the current is. And so a vacuum gauge is actually more efficient in a deeper vacuum than it is when it's exposed to atmosphere. So this is the reason vacuum's used in a thermos, right? When we look at a thermos, it's pretty interesting because you got this silver wall inside a thermos. So we're blocking radiation, we're blocking conduction, we're blocking convection, right? The only place we can have a small amount of conduction here is at the top of the lid, so they try and keep that real thin. If you look at a lot of these new bottles you get, like the drinking silver stainless steel ones, they keep that on like a 1/16 of an inch around the rim because they want to keep that conduction down to a minimum. Right? So vacuum's a poor conductor of heat. All right. So how does the vacuum pump? Well, the gas is, I don't know if I'm not tied to the internet here, so it's not going to work on my slide here, but this is the rotary vane inside here. Literally all it's doing is it's sweeping away. As this thing spins around, it sweeps away the gas molecules, and it creates an area of low pressure, right? And then gases that are in your system shove out of that system and into there, right? So this is what we want to, if I can move ahead on the slide, I might have to move it on my, on here. Because it's saying, sorry, some things are not working. I don't have a mouse here. Let me see.
Plug the mouse in from other machines, yeah?
No, it's just, I just gotta hit OK, and I just can't see my cursor on the screen because it's shrunk. Or it's not there.
Your
There we
cursor's
go.
on the screen, bottom of the pump.
All right, so here's what I want you guys to understand. We got this giant vessel, right? It's got a shitload of molecules in there, okay? It's pushing all directions. Here's what I want you to understand. When that vacuum pump swings around and creates an area of low pressure, the gas is shoved out the line and into the vacuum pump. It's just pushing, right? And initially, we have a lot of pressure, we have atmospheric pressure. So it pushes really hard and it shoves in really fast. Your pump's just hogging air out because it's shoving it through that hose very, very quickly. As the air density drops and this pressure becomes lower, it can't push as hard. So it pushes really hard at the beginning, and then it's pushing, and it's got less pressure and less pressure and less pressure and less pressure, right? And the vacuum pump's just sweeping those gases away and causing the pressure to find equilibrium. So as soon as it sweeps away here, it creates a void, and the gases just want to rush in and fill that void. That's literally all that's happening. This is an extremely important concept to understand in evacuation. If you don't get this piece, you're never going to get past how this science actually works. Because when you're connecting, if you think about what's happening here, this is why large vacuum hoses make such a big difference. Because this is a restriction to push out that air into your vacuum pump, right? The way of thinking of this is, if you went down to Sonic and you got that big fat shake straw, and then you got a coffee stir, right? You blow like hell through the coffee stir, can't get much air through it, right? You blow like hell through the big straw, and it's gonna just force right out. There's no problem, there's no restriction at all, right? You can go right, you can blow as hard as you want on that thing. It's exactly the same way. And as the pressures get lower and lower and lower, the hose becomes more and more restrictive, right? It's just because it's friction, it's all friction on that hose. And it's what we call conductance speed of the hose gets very, very low. So this is where the lost art of vacuum comes into place. 1959, right? And this is like, how the hell did we forget this as an industry? And it goes down here, I got highlighted here. The conductance speed of 1/4 inch OD refrigeration tubing is too small to be used as a connecting line in the system. So we'll not even discuss it. Never use it if you can avoid it, as it's too costly and excessive pump down time. Right, so it's literally 1/4 inch service line what we're talking about here. And when they wrote the book on vacuum, they're saying never ever use this. This is just, we're not even gonna talk about it, it's stupid, right? However, we want to talk about the main reason for explaining this sizing problem is to show the handicap of undersized lines in greatly reducing the pumping capacity of high vacuum pumps, right? So the key thing here is what we want to understand is that with conduction speed, bigger is better, okay? So the maximum obtainable gas, we have three flows. We have viscous flow, we have transitional flow, and we have molecular flow. Viscous flow is like you turn on your spigot in your house, you see the water coming out in a nice laminar stream, okay? It's just continual flow in one direction. When we get to this transitional flow, it's still generally going in the same direction, but it's transitioning to molecular. It's just mathematically changing its flow. And molecular flow is when the molecules are going any random direction. If one of them happens to bounce its way down the hose and get in the pump and get swept away, right, we got a little bit further in our evacuation. But the pressures are so low at the molecular region that there's no direction to the flow anymore. Transitional, we have some, okay? 1/4 inch hose at 1,000 microns. If you have a 1/4 inch hose, and we're talking about 10-foot hose, typically, you know, you got your 2 1/4 inch lines going up and then you're pulling down your center line. No matter what size your pump is, if you have a 50 CFM pump or you have a 2 CFM pump, your hose has a conductance speed of 1/2 CFM, period. That's a limiting factor on your system, is your hose. So if it's got a Schrader core in it, it's even less. 3/8 hose at 1,000 microns has a conductance speed of 1.5 CFM, right? 1/2 inch hose, you guys have all seen the Appian Tez 8, right? Appian has 2 black hoses. Why does it have 2 black hoses? Because it's good for 4 CFM each, okay? And a 3/4 inch hose at 1,000 microns has a conductance speed of 16 CFM. If you go back a couple slides here, this is why this matters. It's diameter to the 3rd or 4th power, okay? This is like the guy that tells you that when you tell him you need a 20-inch return, he goes, yeah, if I put 2 10s on, right? He doesn't quite understand diameters, and that's not the same thing.
No.
Okay? It's diameter to the 3rd or 4th power. So when we start increasing this hose size here, right, it goes up exponentially, okay? And as pressure drops, the flow decreases, and as line size increases, so does the flow. So just to put this in perspective here, our 1/4 inch lines that we use, right, they're about 3/16 of an inch inside diameter. And a true blue hose has got a true 3/4 inch. Now the other thing that, if you get into a vacuum, you'll notice that, like, if you go into an industrial process vacuum, they use all these stainless steel, really cool fittings that are highly polished inside, right? Because they don't want to have any like porosity to that material, so it's gonna hold moisture. Or, I mean, literally, if you've been down, what's the name of the vacuum chamber up in, is it Sandusky, the big vacuum chamber they have up there, big ball?
That one, they have 6 vacuum pumps. When they put the gadget they're gonna send up in outer space, they come up with outer space conditions.
Right.
And then they have a charge and they open up the stuff to see if it'll open up with a vacuum.
Right.
When they videoed it, they said the light bulb lasts 45 seconds because the heat from the light bulb cannot transmit. Yeah. 45 seconds.
And that vacuum chamber is so sensitive that if you walked in and you put your handprint, you touch the wall with your hands, they can register the oil, the pressure created by the oil vapor in your hands on the wall.
Yeah.
So it's literally a sterile clean room in that place, okay? And so we're talking about, just think about your hoses for a minute. When you guys are using, air conditioning, refrigeration hoses, they're full of refrigerant, they're full of oil, they're full of acid, they're full of moisture. If you have POE oil you run through your hose, guess what? You got a film of oil, it's also got a film of moisture. Probably my biggest pet peeve in the industry is hooking up gauges to a system. If you work for me and hook up gauges to a system on part of a maintenance, I'd probably fire you, all right? Because I'm just that adamant that you do not need to hook gauges up to a system to see if it's working right, period. You should never, ever do it. Like going to the doctor, and they're like, we're gonna check your heart. He gets out a scalpel and rips your chest open. It's like, it looks great to me, This is what we're doing every time we open up these systems, and we introduce your hoses. If you don't park them on your hose parks, or use low loss hoses, you are getting them full of moisture. They're literally filling with moisture. And as soon as you blast refrigerant through that, you're blasting moisture through that system. And your dryer can hold a little bit of moisture, but it only can hold so much. And eventually that moisture goes in and it goes out the other side of the dryer. It just becomes saturated. We depend on a dryer to hold some of the moisture, but the poor quality service we're doing, we're seeing compressors and copper plating, that kind of stuff. Well, that's because poor evacuation and poor service practices. So refrigerant hose has low conductance speed. We're too small. And outgasses like crazy. If you ever bought a set of hoses and you open up the package, you smell the rubber smell, right? That's gas, that's outgassing. When you smell something like that, it's emitting a gas, which means if you're trying to draw a vacuum, you've got to remove the gas that it's emitting, right? In fact, Appian will tell you our hoses don't achieve maximum vacuum till you use them about 50 times, okay? Because the rubber material is continually outgassing and curing the entire time you own that hose. Rough interior surfaces on the hose. High adhesion properties, which means that everything in this room right now has water adhered to it. All right, at a molecular level, everything in here is just sopping wet. Tables are wet, ceiling tiles are wet, computer screens are wet, walls are wet, dry boards are wet, everything's covered with moisture in here. It's adhered to the surface. We want to be able to break those bonds of adhesion and pull that moisture out of the system, right? Refrigerant oil contaminated, pin pricked, okay? You guys have all seen pin pricking on a hose. I'll show you an example of that. Those are not one-way check valves, okay? If gases leak out, they also leak in, and high permeation. So when we're talking about flow in a vacuum, okay, we want to be in the fast flow or the viscous flow range. And so when you're looking at the viscous flow range, it's the viscous flow ends at 100 divided by the diameter. So viscous flow ends, if you're looking at that 1/4 inch hose, the reason it takes so damn long to get to 500 microns is because the viscous flow stopped at 533, all right? That's why it takes so long. If we went to a 1/4 inch, true 1/4 inch, it would stop at 400, 1/2 inch at 200, at 3/4 of an inch, it's 133. Now this is an interesting topic because I got on the phone with somebody from one of the large refrigeration manufacturers. And they're like, we're going to use your True Blue hoses, but we're not going to use them. We're going to go a full 1 inch. I'm like, no, good luck with that. Have fun. cause it's not gonna make any improvement. He said, oh, he's like, bullshit, he says, it's gonna work better, I know it's gonna work better, and I'm like, dude, I've done the math, right? You're gonna go from 133 to 100, okay, on the viscous flow region. You wanna pull down to 200 microns, it's not gonna make much difference at all, but go ahead and do your little scientific experiment and have fun with that. So they did it, and they called me back and they said, yeah, you're right, we didn't realize that was gonna happen. Why does that happen? I said, I sent you the math, just review the math again, but I don't think you did. So, molecular flow begins here at 5.33 microns, and transitionals between that 133 and the 533. So the moral of the story here is, we did the math on the true blue hoses. I actually helped design the true blue hoses for AccuTools. So when I did the math on these things, that's what we came up with, right? And there's diminishing returns going beyond that. So everybody goes, well, wait a minute. I get it, okay, get the hoses, gotta be bigger, but what about this damn 1/4-inch ports, right? There's just no way you're gonna get all that stuff through a 1/4-inch port. And you would be right, except that 1/4-inch port's very short, right? If you take a small port, you can blow air like you can whistle, you can breathe through your mouth and you whistle pretty easily because the length is so short. You try and do that through a long hose or a long tube, it's gonna make a big difference. But I want you to think about the density of the gas for just a minute, because when we start, we have 760,000 microns, right? And as we're evacuating, we get down to 20,000 microns, 97% of the atmosphere has been removed at that point, of that free air. At 10,000 microns, 98.7%. At 1,000 microns, 99.87. 500 microns, 99.93% of the atmosphere has been removed, okay? On a 1/4-inch port, if you take a 1/4-inch port, you calculate the area of the port and the length of the port, that port will conduct about 14 CFM of air at 1,000 microns, all right? So because the orifice is so short, it doesn't have a big impact. It's all about friction loss in the hoses. So as the air density drops, if you think about it, initially when you're first pulling down at 0 minutes, there's a ton of cars on the freeway. They all got to sort of bottleneck down. It's just like Broadview Road out there, right? Everything bottles down, you can't get through. But then as soon as the traffic lets up, think about Broadview, right? Right now it's 5 o'clock in the afternoon, this is what we're dealing with, right? In another hour, it looks like this, you can sort of coast through, right? By the time we leave here, there's no traffic anymore. You're just gonna zip right through. It doesn't matter anymore because this is exactly the way vacuum works. It's exactly the same thing. All right? Now, what you gotta remember is there's 3 factors in evacuation. There's the speed of the pump, the speed of the hose, and then the speed of the system that we're dealing with. And a lot of people don't think about this all the time. And there's a formula that just says this, the speed of the system is the speed of the pump times the conductive speed of the connecting manifold divided by the speed of the pump plus the connecting speed of the manifold. It's just like an averaging formula there, okay? Statistical formula. So basically, if we were to take a, and you want to have a pumping speed of at least 4 to 1, right? There's always a loss. As soon as you hook up a vacuum hose to a vacuum pump, there's a loss, period. Can't stop it. The pumps are all rated at free flow, okay? So that 8 CFM pump is 8 CFM at free flow. So down here, I just did the math here, and if I hook up, to an 8 CFM pump with a true blue hose, I have about a 12% loss, which sounds substantial, but that is a ratio of 7.25 to 1. So way over 4 to 1, right? 4 to 1 is desirable, but it's 58 to 8 ratio or 7.25 to 1. You take that same pump at 1,000 microns, you hook it up at, on the conservative side, a 1/4-inch hose at 0.7 CFM, you're now at a 5 to 8 ratio or 0.006 to 1, okay? You lost 94% of your capacity of your vacuum pump is gone. As soon as you hook a 1/4-inch hose up, 94% gone. So, what's the limiting factor? It's not just your speed, you gotta also include your refrigerant line. So then I redid the math here and said, okay, well, 3/4 refrigerant line by 3/8, 50 foot of each, 1/4-inch vacuum line, 5 CFM pump. Do the math here and you say, well, I got a conductance speed of 3.29 CFM on the 3/4 tubing and 0.2 CFM on the 3/8. So you add those together, that's your system conductance of 3.49 CFM. So think about that for just a minute. Almost every line set you guys work with up through 5 tons, right, is 3/4, 3/8. If that's all you work on, you may as well not buy a pump much lower than 3.5, 4 CFM, because you're never gonna use that. Now, if you're gonna connect 1/4-inch hoses to that thing, now you're gonna drop it down to 0.2 CFM, all right? 0.2 CFM. So the limiting factor this time is the hose, because I got a 5 CFM pump. Pump can handle 5, hose can handle 0.2, system can handle 3.49. Now you think going to bigger tubing would be a bigger problem, right? Because you got more volume. But in reality, a lot of times I can pull down bigger systems faster than smaller stuff, because the conductance speed of the system is higher. So I take 1.1/8, 50 foot by 1/2 inch, 3/4 inch vacuum line, 1 meter, 12 CFM pump. The conductance speed of that 1.25 inch tubing is 16 CFM. You know, the 1/2 inch is 0.65, so I got a total conductance speed on that system of 17.3 CFM. This hose is capable of actually 58 CFM. When we rate hose as an industry, we always do 10-foot lengths. This is not a 10-foot length, so I had to adjust it for the length, so I'm at 1/3 of a meter here, so, or 3-foot hose. So I actually conduct 58 CFM. My 12 CFM pump now is my limiting factor, right? So I can pull the system down very, very quickly. So you look at a True Blues hose versus standard hose. I had 3 vacuum pumps from Field Piece, hooked them all up to the vacuum gauges. All of them could pull down south of 10 microns, 5, 4, 8, 7, 7, 7. That's a pre-test. They're all within 3 microns of each other. Now I want you to look at this for just a minute, because this is a 1/4 inch hose, this is an Appian hose, and this is a True Blue hose. So this is time here. This is 0, this is 5 minutes. So this is about 1.5 minutes. The True Blue hose is down at 1,000 and then at 500. These are on recovery tanks, okay? The Appian hose hits it here at about 7 minutes, so about twice as long, and it's 1,000 at 15 minutes. I gave up on this 1/4 inch hose because at 14 minutes I hit 1,000 microns, and you can see it's sort of flattening out. It's going to be way out here sometime at maybe half an hour to get the same thing. So literally 30 minutes for the 1/4 inch hose versus about 2 to 3 minutes, 2.5 minutes to the same thing with a True Blue hose. Literally just increasing the hose size, right? Same 3 pumps, different hoses on there, difference is the flow. So the question becomes, well, how big of a pump do I need, right? I love this because Field Piece just came out with these 10 CFM pumps. I just worked with them a year ago. They had a big change of management. Went through this whole thing explaining conductance speed and hose sizing. They sold a shitload of pumps, and AccuTools sold a lot of hoses. And then they come out with their new pump and they show with a 1/4 inch hose on it. Wow. A 2 CFM pump, believe it or not, is adequate up to 5 tons on most systems. Literally a 2 CFM pump. A 5 CFM pump will be adequate up to about 10 tons, and for larger systems, an 8 to 12 CFM pump will get the job just as fast as a 50. It's not going to make any difference. You may as well never go over an 8 to 12 CFM pump, for even the work you guys are doing on a large commercial and industrial. I did a chiller. I'll show you. I did a 2,500 chiller a year ago, or 2 years ago. The reason is because the refrigerant lines are so small and so long that creates resistance to gas flow. So there's just no reason to go with a bigger pump. You know, Johnson Controls used to wheel out these huge Welsh pumps. You know, I don't know how big some of those things were. They literally took 2 men and a boy to move, and they would hook them up to 1/4 inch hoses, like 6 1/4 inch hoses going everywhere. That was never going to work. Here's in my shop. This is the 2 CFM vacuum pump Navac makes. I can literally hold it in my hand. I mean, it looks like a toy. In fact, Navac came out with it, and they're like, nobody's going to buy this thing. They thought it was a novelty. You know, it only has an hour runtime on it, and I'm like, let me try that on our True Blue hoses. So I hooked up the True Blue hoses. So this is a 12 CFM pump, hooked up like everybody would hook up. A 1/2 inch line going up to the 12 CFM pump. In the manifold, coming out 2 1/4 inch hoses, run up. 12 CFM ultimate pull has a 5 micron, the 2 CFM can only pull down to 10, right? Right up to the manifold hoses. Well, how much faster will the bigger pump be? So, not surprisingly, when we have a ton of pressure in the system, we can push out very quickly. The 12 CFM pump initially is right here. it's pulling down faster, right? It's blowing past till we hit 2,000 microns. 2,000 microns, something magic happened. 2,000 microns, the pump was no longer the limiting factor, because the 2 CFM pump was a limiting factor. At 2,000 microns, all of a sudden the hose became the limiting factor. Just switched around. And at 2,000 microns, look what happened here. This is 7 minutes, right? 7 minutes I'm at 500 microns versus 15 minutes on the same tank, right? And who would think that that 12 CFM pump, if you just went on and you bought a 12 CFM pump and you hooked it up and you paid all this money, hooked up the 1/4 inch hoses, and I beat you with my, you know, it'd be like going out and racing a Ferrari versus a Yugo, you know? And that's literally what it looks like on there. But if you hook a boat anchor to the Ferrari, or take off its wheels, it's just not gonna go that fast, right? So it's faster, but not for long. So the hose size really, really matters. And we actually tested, I mean, I tested, probably about 15 different hoses before we found this hose that actually had, the properties that we needed. And the biggest thing was it didn't outgas. We tried a lot of hoses. Ideal Vacuum makes hoses. A lot of companies make hoses. We tried a lot of them and they just didn't work well because they didn't achieve a low vacuum. This stuff had a super smooth interior. It was really flexible. Could be knocked, you know, back around. It was flattened out. But it ended up being 96 times faster than 1/4 inch hose. And we've never had a hose fail yet out of all the time we've, well, AccuTool's been manufacturing them. So this is, I'll just pass this around if you haven't seen one. This is the hose material. And a hose is so big you can slide a 1/4 inch nut inside that, just to give it an idea here. So another question we get, and I'm sorry I have a video on this. Hey, look at that. All right, what's the function of the pump ballast? Well, here I got moisture, 2-stage vacuum pump. I got moisture going in. It's going into the 2nd stage here. And what I'm doing here is I'm adding air in the side of the pump on the outlet stroke. And what happens is this moisture, when it comes in here, it's as we increase in pressure, you guys have all used an air compressor, right? And as you run an air compressor, water pours out the bottom of the air compressor because we're squeezing the air, it squeezes the moisture out. When we're evacuating a system, exactly the same thing happens. We're squeezing the air down, it crushes it down. No, the water becomes actually liquid. We don't want that on the outlet stroke. So we have a ballast, we open up the gas ballast, it interjects air in there, and then air drives that moisture back out, makes it back to a water vapor, so that it can be expelled by the pump, right? So the ballast is not the knob you crank shut with your pliers, right, and leave it that way forever. You should actually have that ballast open to about 2,000 microns. Now, if you're using true blue hoses, you're gonna blow past that really fast. But if you're on a wet system, literally it'll come down on a flat line like this, okay? And in flat lines, you wanna open up that ballast and let that ballast help remove the moisture from the system. Otherwise, it's gonna emulsify in your oil and the vacuum's gonna stop. So the ballast works from about 20,000 microns down to about 2,000. At 2,000, you shut the thing off because you don't need it anymore, okay? It should be closed to attain ultimate vacuum of the pump. Oops, wrong direction, sorry. So desorption and dehydration. This is so important, okay? This is so important. There's nothing that you can do that's more important than keeping your tubing cap enclosed and nitrogen flowing through it while you're working on it, right? As soon as you open up tubing, like when you go out there and you pull those plugs out, as soon as you pull those plugs out, that tubing is acting like a sponge. It's pulling all the moisture in as fast as it can. It's like, literally if I took perfume and I sprayed it over here in a second, you'd smell it over there, right? So it travels from high vapor pressure to low vapor pressure. It's gonna coat that tubing. And desorption, we have adsorption and desorption. And desorption is the process of breaking those water bonds from the surface, okay? And so what we're showing here, this is 10 to the minus 3/4, this is 1 micron, but when you get into really deep vacuums, what they're doing here is they're removing moisture by K-Cal or by ultraviolet light, right? And it's just showing the rate of desorption on the graph here. But once the pressure is in the low micron range, here's what I want you to understand: 99%. Once we're down to 500 microns, 99% of the load in the system is moisture. All the air is out, all the oxygen's out, all the gases are out. It's literally 100% water. It's 99% water we're pulling out of the system at that point. Because water vapor bonds are breaking and we're pulling that moisture out of the system. For HVAC system, most of the surface moisture can be removed in pretty short order, as long as it's not excessive. So here's what guys don't understand, okay? Because you go, oh shit, volume of the system is pretty darn small. It's not that big of a deal, right? It's not that big of a deal. There's not that much gas to remove. If you were to like do the math and calculate the inside diameters of your tubings, you only have a cubic foot or two of maybe 3 or 4 cubic foot in a 5-ton system, the total volume, right? You go, well, 5 cubic foot, 5 CFM pump, 1 minute, should be down, right? It doesn't work that way, right? Because in 1 minute, you do have, seriously, think about it, going back to the other thing I was showing you, we have 99% of the atmosphere out, right? At 20,000 microns, we got 98.7% of the atmosphere out at that point. But all the moisture just keeps those bonds keep breaking. So what's happening here is if I have a teaspoon of water that weighs 0.0092 pounds, at 212 degrees, right, and atmospheric pressure, that water would occupy 0.24 cubic feet of water vapor. Now there's something weird happens when we cool gases down. As the temperature goes down, the specific volume goes up, okay? So at 32 degrees, it's now 30 cubic foot. It went from literally 0.24 to 30 cubic feet of water vapor. This is why we don't evacuate systems in the wintertime, right? At 20 degrees, it's 51 cubic feet of water vapor. At 0 degrees, it's 138 cubic feet of water vapor. Think about that for just a minute. From a quarter foot, 0.24 cubic feet to 138 cubic feet, just by reducing the temperature down. And it's because the water vapor is sublimating, and it's at that point it's building up vapor pressure very slowly, and it takes a tremendous amount of space up in the system. All right, this is a graph here. This is out of the review of action for service engineers. The other thing I want to show you here, and the reason this one's so important, I have a ton of guys in the industry. I hit 500 microns, I valve it off, and it's good enough. Well, I hit 500 microns on that graph 1, 2, 3, 4 times. And that system's sopping wet. Because every time I valved it off here, you see, first of all, you see this fast rise in this curve. When it curves off like this, what that's indicating is that curve is tailing off as it's building up a vapor pressure, and it's eventually going to equalize. Second time I pulled it down, it took longer than the first time. That meant I had some moisture. I removed some of the moisture in the system. Notice this is 15 minutes, 30 minutes, 45 minutes. Now we're not pulling that vacuum down literally in 7.5 minutes down to below 100 microns, because the system's soaking wet. All right, this is what happens when you get on a wet system. Is all bets are off, because now you're going to take what took you 7 minutes, it's going to take you maybe 7 hours, maybe 7 days. Longest evacuation I had was probably a little over 30 days. I was evacuating. I went down to PG&E in Barberton, and 2 chillers side by side, piped in parallel, no valving to shut off the second barrel. Compressor went bad. In the fall, contractor pulled the compressor out, left the piping open.
Oh, shit.
And the 55-degree air going through the barrel, right? Filled the barrel full of moisture, condensation. So we blew out as much as we could with nitrogen. And I remember getting on the job, I got out there and he said, yeah, it's down to 500 microns. I valved it off, and it's just, gauge is going up. And well, it's wet. Put my vacuum pump on, water turns milky, oil turns milky, it's full of water. Get a dry ice trap to try and pull the moisture out with a dry ice trap. 30 days to get the moisture out of the system, right? Finally gets I think it was a 75-ton E-compressor. You know those machines have 275, 150 ton. Start the compressor up, and it goes, oh, son of a bitch. Brand new compressor, we're out there doing factory startup for train. So I'm like, what in the hell happened? So I heard something go down the line. I pulled the end valve off, the service valve off the compressor, and the dryer is literally it was a solid core Sporlan dryer, it's literally sand. And the whole inlet to the compressor, luckily the screen stopped it all, it didn't blow the screen out of the system. I'm like, son of a bitch, I've never seen a dryer exploding like that. So I pulled the dryer core shell out and pulled a t-shirt. Luckily the foreman for PG&E was out, or PPG was out there with me, and it said, Comfort Cooling Systems. The guy put his own, he raised this new dryer on.
That would keep the moisture from getting
And
in.
he put a rag in there.
And left it in there.
And then put the cores in. So I was evacuating this wet rag for 30 days, along with all the other stuff. And so these kind of things, though, hitting 500 microns is not enough. So let's talk about the evacuation process. All right, there's nothing you can do that's more important than keeping the tubing clean and dry from the start. That's honestly, if you want a fast vacuum, that's what's gonna happen. You wanna always sweep. This is the biggest mistake that we're making in our industry today. The biggest mistake. Nitrogen, our air is 79% nitrogen, right? Everybody knows that. If you have a system that's been open to atmosphere, and you go, you know, like let's say we're doing in fact, the last one of these that I had a big problem on was a big variable refrigerant flow system. Had, you know, I don't know, maybe 100 heads on it, right? Guy goes out and he puts all this piping, he's got miles of piping in it. So they go from the factory, we're gonna test all this piping. They take the pressure up to 600 PSI. Now, if you think about, if I got a sponge here, and it's holding the air molecule and it's holding some moisture, right? And I squeeze that sponge down to 600 PSI, I'm gonna wring the water right out of that air, and I'm gonna drop it out, and it's gonna drop out as liquid. When it drops out in liquid, the only way to get moisture out of a system that's a liquid is to change it back to a vapor again, right? It's not gonna suck. There is no, the way to think about this, if I took a Coke bottle and I dropped just a cotton ball in the bottom of the Coke bottle, I tried to suck that Coke bottle, the cotton ball on, it's not gonna move. It doesn't care. It's just stuck down there because there's no flow in that Coke bottle. There's no flow in your air conditioning system. When you start drawing a vacuum, there's no flow in there. There's nothing that's gonna carry that moisture out. You're not gonna suck it from one side to the other. It's just a reduction in pressure. That's all it is. You keep reducing the pressure, reducing the pressure. The flows are so low that it's not gonna carry any moisture with it. So eventually it's gotta boil off. If you don't purge all that air out of that system before you pressurize it, the moisture will fall out, okay? So big mistake we're making when we're changing out compressors, when we're changing out coils, when we're changing out piping, is not sweeping that system. And when I say sweep it, I'm talking about less than 20 PSI of nitrogen. Just push the air out of the system. Purge it out for a few minutes. Let all that air get out of there so you got it replaced with dry nitrogen. And then raise your pressure up and do your pressure test. Okay? You do not want to pressurize it first. After you do your pressure test, you vent it down to about 1 PSI. You do not blow all the atmosphere out of that system. You leave a small amount of pressure on it. And then, obviously, clean vacuum pump on your oil. We're going to perform a single deep evacuation. This system here, I'm pretty sure it's the same slide. I'll get to it in just a minute. The first time I tried this hose out, it was actually went out and met Mark Jackson's company, Jackson Comfort Systems, on a job. We had 100 foot of 3/4 3/8 on a 4-ton coil, existing line set. They did an R11 flush on it, purged it with nitrogen. It was dry when I got there. Went out to do the video with field piece, and it came down so fast. It came down so fast that I had the videographer stop the video and say, there's something wrong here. There's just no way this happened. I had to go, guy, get the tank of nitrogen, we purged it again. Because we're literally taking vacuums that took an hour, and we're taking it down to less than 1 minute. You know, we're less than 2 or 3 minutes, you're down south of 200 microns, okay? This is what we forgot as an industry, is just how to do this stuff. You're gonna pull a single fast evacuation, so down, isolate. When I isolate it here, this is leveled off. This is 20 minutes later. It only went up to 239 microns. All right. You will never, if you're looking at if you buy a AccuTools vacuum gauge, it's going to drive you freaking crazy, because you're going to realize very quickly that it never ever stops rising. It might, you know, a day or two later, but for a full day, if you were to evacuate a tank down today and watch it for a whole weekend, it's going to continually rise all weekend long, because those bonds of moisture are breaking away. As they break away, they create vapor pressure in the tank. And the vapor pressure is continually rising. You're going, whoa, why am I not seeing that in all my other gauges? And it's because they hide it, right? A lot of vacuum gauges go, 500 microns, 250, 100, 50. You don't see all that stuff happen. These have a 1/10 of a micron resolution, so you're gonna see things you'd miss otherwise. Vacuum pump oil, right? This is $45 a quart, this vacuum pump oil. Extremely low vapor pressure. Believe it or not, if you buy a medical grade pump, or you buy Navac, this company, their company, actually a Chinese company makes pumps. Actually, 80% of the pumps that come into the US market, believe it or not, are made by Navac. And you buy their standard vacuum pump, and you buy the medical grade vacuum pump, that's the difference. Right there's oil. It's literally the difference. That oil has a very low vapor pressure. It'll pull down to less than 5 microns at 100 degrees Fahrenheit. It's got a very low, and this is what's gonna make your pump achieve deep vacuums, really. It's just, refrigerant oil can't be used for vacuum. It's just highly refined oil. That's all it is. Just very, very refined oil, and that's what makes the pump work. So the higher quality vacuum pump oil you have, the lower you can get your vacuum. This also is what they call hydrophobic, I believe. So it also doesn't hold moisture. It liberates with the moisture. So like when your vacuum pump oil gets milky, it's because it's emulsifying. It's mixing with the oil. You'll very rarely see this emulsify. So if you've ever gone to like a college, or you've gone to like a medical facility, they have the vacuum pumps that are running, they're literally running 24 hours a day, 7 days a week, and you go, how the hell can that thing run without they're sucking all kinds of nasty shit down there, from the labs and stuff, and you're thinking, how can this thing run for so long without an oil change? That's it. It's $45 quart oil, right? And this high quality vacuum pump oil makes a big difference. You want to make sure you're pulling the quarters, okay? A 60th gallon pump with a core in, that drops down to 0.2 CFM, right? That's pretty much it. So you can just see the big diameter difference right there. Dedicated vacuum hoses, right? Again, these are pinpricking. Pinpricking in a hose cover permits trapped gases to escape the hose carcass. And the reason this is a carcass is because this is dead technology. Don't use it anymore, all right? Steam, air, other gases permeate, slowly pass through the tube and build up to the reinforcement, and the manufacturer must pinprick it to avoid getting bubbles in the hoses. These are not one-way check valves, right? These leak out as well as they leak in. Its leak rate is what we're concerned with, okay? I know nobody in this room needs to hear this, but you gotta have a vacuum gauge, because you can't tell the difference between 29.14 and 29.96, and that's the difference between 20,000 microns and 100 microns. Your eye, that's the width of the needle, right? It's more than the width of the needle. Back in the day, right? In fact, I remember when I was talking to guys at EMS, that was a big thing. If you don't have a vacuum gauge, how can you tell when the pump's got a deep enough vacuum? Sound of the pump, that was a big thing. Remember?
It came out of a textbook, I can't remember which one.
Yeah, it was the one right after they forgot everything you knew about vacuum.
Right.
Right? And honestly, God, I've seen more bad stuff in textbooks, so you can't rely on a textbook. The sound of the pump won't tell you the difference between 20,000 and 100 microns either.
Or put the discharge from the pump into a cup of water, and the bubbles, see the bubbles come out.
When the bubbles stop, you're done?
Yeah.
Never
A lot of it's pulling water.
Haven't tried that one. You have to
So
try
the
that.
pump shuts off and it sucks the water.
Yeah, well,
Well, at Tremco, we had absorption chiller, and absorption chiller boils water at 40 degrees at 1/100th of atmospheric pressure. So they had to run the pump periodically to dry it out. And that's what we do. Out of the pump into a glass of water, and when it started, the bubbles are, and you run it till the bubbles stop.
I have to try that one. That's a new one for me.
Isn't that kinda how the purges work on a 19B?
Yeah.
I don't remember water being on it though.
Yeah, that's an interesting one. You can't discount. I mean, that's back in at points in our industry, like if you look at the old vacuum gauges for doing chillers, they used to have almost like a refrigerant, it would change the temperature as you were pulling the vacuum, it would change the temperature of the gauge. Can't remember what it's called, the void gauge, or what the name of the gauge is. There's a lot of different ways of testing for vacuum. The challenge is all the gauges they were inaccurate, you know, there's a lot of challenges with measuring deep vacuum. This is about the best way to go today, is a digital vacuum gauge.
You ever deal with Nash pumps? That's what they use in hospitals for.
I drove a Nash once. So, but never dealt with a Nash pump. Yeah, no, those are, now there's things
Water seal.
we've forgotten about in our industry, but anyway, high accuracy, high resolution, temperature compensation, this is the big one people don't think about with instruments. A lot of the tools that you're buying today are not temperature compensated, and manufacturers are just starting to do this, meaning that when you buy a tool and you look at the specification, it'll give you an accuracy spec, it'll tell you it's plus or minus, let's say, a PSI at 75 degrees Fahrenheit, right? You go, oh, it's a pretty nice tool, and then take it in, you're working in at Stouffer's Frozen Foods in the freezer that's 40 below, and you're just standing there and the gauge isn't hooked to anything, and you're watching it, and it's going from 0 PSI to -1 to -2 to -3 to -4 to -5. It's because you're using strain gauge technology, and as that sensor in there gets colder, it's shrinking down that strain gauge, and it's thinking that it's reading the pressure, when in fact it's just seeing a change in temperature. And they can actually have chips in now that actually measure the temperature of the sensor, and then they say, okay, we know if the sensor's at 40 below 0, that we gotta offset it by X to take it back to 0 again. It's called just temperature compensation circuit. Very important when you're looking at accuracy of gauges. In fact, if you remember the old thermal engineering gauge, you guys remember the old, I think it was 140/57
I
gauge?
still got one.
Yeah, it was a great gauge, but the thing is that you remember you had to go into the
Temperature
dial.
calibrated every
Yeah,
time.
you were the temperature compensation, so you turned it on to calibrate, you turned it up to match the thermistor setting, and then if it changed at all, if the temperature changed, you had to turn it back to calibrate and recalibrate it again for the air, right? Now we do that electronically. This is probably my biggest pet peeve, also, aside from doing the incorrect purging, is connecting your vacuum gauge. This is lovely. This is, you know, I don't know why they decided you need 6 feet of hose, but that's what they decided. So you got 6 feet of hose, he's got it connected to a core tool, and he's got a 1/4 inch hose, and he's measuring a vacuum a mile away from the system, right? Not a good idea. This was designed, the 4-port manifold with a vacuum gauge built in was designed this way because marketing was overtaking engineering, okay? Not a good idea. We don't want to measure vacuum here. A bazillion leak points on this thing. And the vacuum here and the vacuum in the system is 2 different things. And then also, you know, people don't want to measure on their gauges. Just avoid that if all possible. And these gauges, when you see them built into pumps, it's literally to test the pump. It's not the pressure in the system. Right? So you want to attach your rig like this. Okay, in this case here, I'm doing a chiller. This is a 2,500 ton chiller. 1 hose. 12 CFM pump. That hose takes 58 CFM. I don't need 2 or 3 or 4 hoses. I can do it with 1 hose on the system. Okay? Valve cores removed. Direct connection to the pump. Core tools to isolate. In this case here, I had a valve here. I can isolate the vacuum on the bottom of the chiller. Get or a gauge connected like here directly to the core tools. Okay. Here we're doing 2 hoses. I found a lot more experience now. 1 hose will do the job just as fast as 2, because the limiting factor is the speed of the connecting tubing. Pulling from both sides of the system is not going to go any faster. So you go, well, what about the metering device? It's so short it doesn't make any difference.
So where would this actually be located in?
So today I would always evacuate through the suction line, which has the highest conducting speed, and put the gauge on the liquid line.
Okay.
Connect right. That gauge
Sure
can
you
handle.
want this as far from the pump as possible?
Yep, yeah, that gauge can handle 1,000 PSI. You can actually handle over 2,500 PSI, the hydrostatic test.
Oh, if somebody
How do you
accidentally
clean
leaves
this?
it on?
Oh, just
With,
a little bit of alcohol.
so, okay.
Yep, alcohol switched around, rinse it out. Right? So deep evacuation method, right, we're gonna vacuum the system to at least 2 times the level decay. So if the manufacturer tells you 1,000 target, take it down to 500. Ideally, believe it or not, I pull everything down below 100 microns today. There's absolutely no reason not to. It'll pull down so fast, it's ridiculous. So, and this is on new systems. On stuff you're servicing, there will be times, I'm just telling you straight up, with a 410A system that you've had open for service, you're gonna be hard pressed to get under 1,000 microns. You'll evacuate all day, it's just gonna stall on you because the POE oil is like a moisture magnet. It's gonna go into the system. You cannot remove moisture from POE oil with a vacuum pump, period. It requires desiccant dryer, so it's critical on 410A, you always change the dryers out. You've gotta change the dryer. I actually take, after I change my dryer out, while I'm evacuating, I actually take a torch and I warm my dryer up or heat gun and get that dryer up to around 300 or 400 degrees if I can. Get the housing warm just to where I'm not burning off the paint. But that's how they dry out dryers when they're manufacturing, is they bake them in an oven and they dry the moisture out of the dryer. That'll help dry that dryer out, because the dryer is the only thing that's gonna pull that moisture out of the POE oil. It is all that's gonna do it. A decay test is used to determine if the system's been dry. So in this case here, when I pull this down, and this is literally 7 minutes on the system, that flat line, that's the way it should look. When you isolate the core tool, it's just literally flat line. This is a little flip here, you see where I isolated, but it flat line. This is a wet system, okay? This is 1 hour and 15 minutes versus 5 minutes, right? That's what we deal with when we don't do the moisture properly. Triple evacuation, this is a sweep method, dilution method, blotter method. It don't need it anymore. This was back in the day when we didn't have pumps that were 2-stage pumps. We had to use this triple evacuation method. This is out of Carrier's manual. Evacuate your 30 inches, which was about 29.72. Waited 15 minutes, broke it, waited an hour, vacuumed down. So literally 2 hours and 45 minutes, 50 minutes to evacuate a system, right? This is just not something we need to do anymore. People ask about it. Water vapor, right? Nitrogen's not a sponge, okay? It does not absorb moisture. You can't like go, ooh, I'm gonna inject some nitrogen in there and it's gonna just magically suck the water out of the system. Doesn't happen. If there's water vapor in there, it will entrain the water vapor and carry it out. But the nitrogen will not suck the moisture out of the system. If you have standing water, it's not gonna happen, you're not gonna remove it. Water vapor molecules simply reside in empty space, right? When the air is compressed, it cools the water molecules that fall out, right? When air is heated, the space gets bigger and there's more space for it to reside. But water vapor and air are two gases are completely separate. And this goes back to what I was telling you earlier. So we compress that down, we're gonna squeeze the moisture out. Properties of moisture, right? There's water cohesion and adhesion and absorption. Basically, what we're talking about here is cohesions when you got standing water, sticks to water, like cohabitation, cohesion, right? Adhesion is water vapor sticks to the walls of the tank, all right? The process of degassing is the oxygen and nitrogen removal. This causes the dehydration. The water sticks to water, so that's a cohesion. Absorption happens at the surface. Right, lowering the vapor pressure breaks the bonds. Heat of vapor and heating that's up will help break the bonds. So a lot of times we can apply heat to a system that'll help evacuate it faster. So again, why we don't really want to evacuate equipment in the wintertime. You can't break the bonds of adhesion and absorption. How low should you go? 1959 again, right? Finishing pressures of 1 to 200 microns are desirable to make the air in the system so rare that there's only an insignificant weight of it left for the refrigerant to absorb, thereby establishing good control over the head pressure of the compressor, right? So this was a system that we did. This was the one I did with Jackson Comfort Systems, I believe. This was down to 100 microns in 12 minutes, right? 100 microns in holding in 12 minutes. Comfort cooling installations, I recommend 100 to 200 microns. 500 microns max decay. Equipment service, you're lucky to get 250 to 500 with a mineral oil. It's pretty easy. With POE, you're not going to get down much below 1,000. General refrigeration, same. They're ultra low. You guys used to do cascade systems. I know, Mark, you guys did those. Those require require, very low vacuums, down 50 to 100 microns, sometimes even less, all right? Can you vaporize compressor oil? This was one I hear all the time. JB's got some great wrong information out there on this. They're like, never pull below 200 microns or vaporize the oil. Well, no, you can't. You can't vaporize the oil. If you ever want to find out yourself, just go get some POA oil or go get some mineral oil and pour it in your vacuum pump and put your vacuum gauge on it. You'll see it'll pull down to 50 microns or so, or maybe 100 microns, right? The oil can pull down to 100 microns, that means it's not vaporizing at 200 microns. In fact, most oils you can't even evaporate at 30 microns, so this is a non-issue, all right? Isolating the vacuum rig, this is just a little test here where we're closing off the pour tool on there. And actually this is Rudy Leatherman, you guys know Rudy passed away, I'm sure.
Yeah.
So, but again, finishing pressures of 100 to 200 microns are desirable. Leak rate, these gauges, the Pro gauge has a leak rate indicator on there, and the permissible leak rate is about 1 micron per minute, all right? So again, this was out of the 1959 books. And what will happen is you're gonna have it's gonna go up quickly, and it's gonna tail off. And when it tails off, is when we wanna get that leak rate down below 1 micron per minute. So this is probably one of my favorite features. I actually designed the application for this, and what I didn't realize my entire career was I sucked at math. And I figured it out later that when they were telling me about logarithmic graphs in school, I should have paid more attention. Because when you take a linear, you take a line, a linear graph, you think about a micron gauge, it's 760,000 microns. So you need if you were to put that on a chart, you need something about 6 feet tall, right? You need a 6-foot iPad screen so you can see it come down, which is not very practical. So somebody said, you know, if we're gonna have this really tall iPad, we should just scrunch it down and we'll make the graph logarithmic, which means that you're gonna have from 760 down to 20,000 microns is this big, and then it goes from 20,000 to 10, and then 10 to 5, and then, you know, so you end up at the bottom, you got this big long spot, but it's from 0 to 200, right? Which is the same as at the top of the gauge from 20,000 to 760,000. So what happens is that when you squish that graph down, it's got a curve. So it naturally makes a curve, right? So when you're looking at, when you're on Facebook and you're looking at these graphs, you know, pay very close attention to the scale, because it might look linear and it's really, or they might say, well, it's trending, it's flattening out, and it's like, well, bullshit. It's still going up.
Pressure
going
drop
down.
curves for chiller barrels not always that way. You just got to look at the notation on the
Yeah, they're
on
all
the side because they're not linear.
So in the app, when you press this button, this valve down here, and isolate it, I had the guys change it from a logarithmic to linear. So this is a linear graph right now. As soon as it goes to linear, now I can see that if I have a leak, as soon as I isolate it, this is the only reason this is not straight up is because it's over time, right? Otherwise, this would just be a straight up leak, okay? When you isolate and you have moisture, it tails off like this. And this tailing off is just a buildup of vapor pressure. Notice where that's tailing off at around 2,600 microns. Water vapor is going to be somewhere around 1,500 to 2,000 microns, depending on the atmosphere, or depending on the temperature, right? The colder the temperature is, the lower this is going to be. The higher temperature is, the higher this will be, because we can hold warmer air can hold more moisture. All right. So notice that also the decay rate. This is almost a constant 42 microns per second. This one tailed off to 0.8 microns per second. So you'll notice is that if you have a leak, it's going to be a very constant decay rate, like 35 microns per second. It's going to be 35, 36. It's just going to keep going up, and it's not going to slow down at all until it crosses. And I say when you cross about 10,000 microns, you can pretty much be assured that it's a leak, right? This tailing off tells us that it's 100% that it's moisture. So at the end here, we'll pull it down. This was, look at this, 1, 2. This is this is the one we did Jackson Comfort. So 100-foot line set, 4 minutes. We're down 200 microns and holding, right? So the results, way faster evacuation time. This 2,500 ton York chiller, it's about the size of a school bus, okay? 30-inch suction elbow, 1/4 and 3/8 hoses is what they were using on this. They bid 4 to 6 days for the evacuation. That was pretty typical for these guys to do 4 to 6 days. We went out with a single true blue hose and we had it down in 17 hours. Now the manufacturer called for 1,000 microns, right? And I started this in the afternoon, I came back. We were at 121 microns at the pump and 300 microns at the far end of the barrel. So 17 hours. Now we probably could have evacuated that chiller to get down to these levels. We were probably done in 5 hours and didn't realize it, right? So imagine doing a 2,500 ton chiller in 5 hours, 6 hours. And that's what we did with this 17, because we did it overnight, came back the next day because we're thinking, oh, there's no way it's gonna come down that fast. Well, it did. Right, residential systems, this was that one, 5 minutes down below 200 microns. Oxygen and moisture are the absolute enemy, all right? These bearings here, these are not copper plated from the factory, okay? That copper plating came from copper from the system. They got stripped away from the copper line set, floated around with the refrigerant oil, and they got smashed back in the bearings. When we get compressors that are tight, you know, and you go get the 5-in-1 or the hard start kit or whatever, you better be looking for moisture in that system because the bearings don't get tight on their own. Things actually loosen up, not tighten up. And when they're tightening up, that's when we have problems with copper plating in there. And the only way you stop this, the only way you stop this is with a dryer. You've got to pull the moisture out of the system. The compressor is a chemical plant. It's literally from the day you start it, it is a little tiny chemical plant, and it's just making acids and sludge and all kinds of crap, and the rate that it's produced depends on the amount of moisture that you have in that system. The more moisture you have, the more oxygen you have, the more chemical reactions you have, the more problems you're gonna have, right? This is the big one we're hearing today. Oh, these new evaporator coils suck, they all leak, you know, and you have guys taking tons of them back. Well, guess what? It's called formicary corrosion. It takes place when you have oxygen, water, copper, and organic acid, okay? This actually happens from inside or outside of the system. So these crappy evacuations we're doing, that's what's causing this. You guys remember Copeland having the compressor additives and all the TXVs going bad, right? Copeland had a compressor additive. There was a rash about, I don't know, maybe 5, 6 years ago, TXVs just failing everyone. Thousands of them. Residential systems, thousands of TXVs failing. Copeland put a rust inhibitor inside their compressor oil, right? They're like, this will be good, I have this rust inhibitor, this is awesome. They tested it for 2 years, no problems. Roll it out in the field, it's like the shit hit the fan. Why? Well, because the guys at Copeland, they know about evacuation. They evacuated every system before they put the stuff in, you know, they tested it, it works great. The guys in the field, they're gas and go guys. They're not evacuating. They're cracking the service valves open. There's so much moisture and stuff that that chemical plant takes off, and it's actually building up wax and all kinds of other crap that's plugging up the inlet screens to these TXVs. Copeland never saw that coming, right? So these kind of things happen when we don't have good evacuation. Ants nest corrosion, chemical reactions inside the systems that take place, and we can avoid it just by doing a proper evacuation of the system. Some additional notes, right? Vacuum gauge maintenance, that's that little thermistor. It'll tell you when it needs calibration. Just take a little bit of alcohol, pour it in, put your finger on it, swish it around, put it on the vacuum pump, it'll tell you when the calibration's good again. Right?
Did that one say soon?
Yeah, it says soon, needs calibration soon.
Oh.
Yep. Everything in our industry leaks, everything. Even true blue hoses leak, the core tools leak, everything leaks. It's leak rate we are concerned with. Your true blue gauges or blue back gauges are so, the resolution is so high that you're gonna see things you've never seen before, and it's gonna drive you crazy. Whenever you're testing a system, here I'm testing a vacuum rig, okay? You can see I've got it hooked up to the vacuum pump, one hose hooked up to the vacuum pump, and I've got a vacuum gauge here on the end of the pump. I've got a second hose connected off the top of the pump, and I've got them teed together. So at the far end of the pump, I'm reading 24 microns, and at this end, I'm reading 19 microns, okay? Well, first of all, why is there a pressure difference? Because there's always a pressure difference. It's higher pressure at the far end of the hose than it is next to the pump, otherwise pressure wouldn't flow. It's gotta go from high to low, right? So, and while this is running, eventually these two will converge. It'll get closer and closer and closer, but this is gonna take hours, okay? This was probably running that pump for an hour before it got down to this 20 micron level, right? We run them down at trade shows all the time. Once we get the hoses dried out, we can pull these down all day. We pull down south of 10 microns. But you can't close that valve on the side here. This valve is not a vacuum rated valve. It's a blank off valve. It's not meant to hold vacuum, never was. You isolate with it. If you were to buy a vacuum rated valve, you would spend about $300. In fact, your valve will cost more than your pump for the most part, all right? And obviously they're not gonna do that on your vacuum pump. That's why we have core tools. And guess what, core tools leak, but they don't leak near as much as the vacuum pumps do. But it's the leak rate we're concerned with. So what I wanna make sure is that when I hook up my hoses here, that my pump, I don't have significant losses on my pump. Typically, if I say my pump will pull down to 50, then my hose should go down to no less than 100. If my pump will pull down to 25, I wanna see my hose get down to 50. If my pump will pull down to 10, I wanna be down at 20. This pump will pull down around 19, 20 microns, and I'm down at 24 microns here eventually, okay? But that's how we test the rig on there. So why would you wanna use these types of hoses? Cause they're a lot faster, low permeation, low adhesion, engineered for vacuum. It's the first vacuum engineered hose in the market. So that is it. I also, by the way, the Review of Vacuums for Service Engineers was such an important book. I actually tracked it down, bought it, and stuck it together. Bought it and republished it. So I brought copies of it for all you guys. And I rewrote it also. The original stuff is all there, but then I rewrote the back of it with Brian Orr. We did some illustrations. You can have one.
Probably read it.
We did edits on it, so-
Try it as a coffee or a placemat.
Yeah, she's got it. It's in the same binder for Bible. She's got her Bible and a Review of Vacuum for Service Engineers. She spends equal time in both, so.
You got pretty pictures.
Yeah, I put in color in the back.
You got one for Gary?
Oh, sure. So what I did here, in the back of the guide, you'll notice if you get back towards, and this is probably, somewhere back around, page 152 or so. I have a lot of different illustrations of what you'll see in a vacuum with the, who wanted this?
Yeah.
Did you, you needed one down there, didn't you?
I got one.
Oh, did you? All right, good. So, a lot of different characteristics of what we saw in a vacuum as we were doing testing and stuff like that. That's the original 1959 version. The whole front of the book is all the originals, all unedited. It's what we took and redid the illustrations. We redid all the text, made it all readable. If you need a giant copy, I could even print one for you in 8.5 by 11. Just we have it, you know, that size. But I want to keep the book is originally that size, that kind of binding. I wanted to sort of keep it for the history. So. Anyway, so now you got a copy of the original guide. It's very interesting to read, believe it or not. There's a ton of good information in there, but it's like a piece of history we don't want to lose, so. All right, anything else? Any questions? Hopefully this was informative, helpful.
I got a question on those clamps.
Yeah.
What's up with the clamps? I mean, it's just for the different.
So what we did is the, I went and looked at, in the vacuum industry, uses these clamps for evacuation. These things literally only have to touch. So believe it or not, like, and we made it so you could change the fittings out with 1/2, 3/8, 90-degree fittings if you wanna go around the corner or whatever. The fittings pop, you don't have to take them off, but you can leave it, you know, you can, and there's a fitting on the top here, this is called the centering ring. So you can't tighten it beyond the centering ring. As soon as it's touching here, it's sealed. So if I drew a vacuum on this hose right now, I don't even really need a clamp on it. The only reason you need a clamp is it's annoying when the fitting falls off and there's no vacuum. So these clamps these are standard clamps you'll see in the industrial process vacuum. So when I came up with this design, when I worked for, Thermal Engineering, was a company that made the vacuum gauge that you got on your truck, used to make vacuum rigs for the, refrigeration market. This is literally all the height this has to be, just enough that it holds it on. Yeah, just snug, okay? So they had these giant hoses for the vacuum market. I'm like, this is the stupidest thing I've ever seen. Why would you have these big hoses? I didn't understand all the science at the time. I saw this in the factory, and I asked the guys why they did it, and they said, because we always did it that way. Right? That's the way they want them. So they were selling these vacuum rigs. They're selling them to Maytag, and they're selling all the refrigerator companies. And they're literally pulling refrigerators down in 20 micron range. So when I saw this, I'm like, this is what we need for the air conditioning industry, because I ordered a hose from Ideal Vac, because you can order all these pieces, you can actually make your own hose. Thing is, it's cheaper to buy assembled hose. They're actually doing this miles at a time, and this tubing performs a lot better. So we started working with AccuTools years ago on product and design stuff. So I designed this hose for them, and that's what I've been playing around with. So it's a very effective design for them, you know, for this kind of work, and they've been doing really well with it. And it's really changed the industry. They've probably sold, I don't know, 18, 20 miles of hose since they started selling it. So,
Hey, Jim.
yeah. Yeah, is that the original 1959? Yeah, yeah. So, did you get that in grade school?
Probably.
Yeah, so. Yeah, but that was really, that's the definitive, I saw that idea in your office when I was here last time, it was tucked in the corner, so. Yeah, but, anyway, well, if you got any questions or any, the book's well worth the read, and, you know, hopefully got a little bit out of the class tonight, so. Learn something new maybe.
Now, if we trade in our Appian hoses, we get like a discount.
Who's happy on hoses?
Actually, those hoses are only good for about, all refrigeration hoses, even your standard hoses, you should replace them. Like standard service hoses, every year you should get a new set of service hoses. And those Appian hoses are good for about 5 years. And once they're 5 years older, you may as well throw them away. All those hoses, they start to break down, and they start to leak, and honestly, you should be changing your hoses every year. Some guys will say, I use the same hose for 20 years. Like, well, good for you. Especially, you know, the hoses do break down. So it's just, I've been around this for a long time. Seen it fail. So, all right, well, that was all I had.
Thank you, Jim.
Thank you, Jim.